Hello, welcome to the section 5.5 video lecture. So what we're going to do today is one of the more important things we're going to talk about in chapter 5 and in this class. Similar to how the chain rule is kind of a vital rule to be able to do more complicated derivatives, what we're going to talk about in 5.5, the substitution rule, is imperative to be able to do more complicated integrals. So far, the only integrals we know how to find the value for are without having to use Riemann sums are anything that can be written as a constant times a variable to a power and some very specific trig functions. So in this section, what we're going to look at is we're going to look at a rule that will allow us to expand this quite a bit, to be able to do a lot more integrals. So you can go ahead and take out whatever you're taking notes on. If you've printed out the notes for section 5.5, and if you want, you could be using those. Once again, they can be found under handouts page on my MATLAB, and turn to page 27. So in back in section 4.1, we define the indefinite integral using this notation. So the indefinite integral is equal to of f of x is equal to the antiderivative of x plus c. An important distinction between definite and indefinite integrals is the definite integral is a number and the indefinite integral is a function plus an arbitrary constant. So what we've been doing in the previous couple sections is finding a value, a number, whereas here what we're going to do is find a function, similar to finding derivatives. In previous sections, we've been able to find antiderivatives of easily identifiable derivatives. The substitution rule is going to allow us to go beyond that. So the substitution rule says that if u equals g of x is a differentiable function whose range is in an interval I, and f is continuous in I, then the integral, indefinite integral of f of g of x times the derivative of g of x dx is equal to the antiderivative of f of u du. So how do we use this method to evaluate indefinite integrals? Well, the idea is we substitute a u for g of x. So, and we're going to substitute for du for du dx, which will be g prime of x dx, to obtain an indefinite integral f of u du. And then we're going to integrate with respect to u and replace u by g of x at the end. So here's the idea. So here's somewhere I go ahead and tell you what we want u to be. So if we look at the first example here, we've got a u, and we're going to say that's x to the fourth plus 1. So what we want to do now is we want to find du. Okay, so go ahead and find du. So we find the derivative of x to the fourth plus 1. So du would be 4x cubed dx. Okay, and now we can, if we look at this function, if I rewrite this like this antiderivative as 1 over x to the fourth plus 1 squared times 4x cubed dx, what we can see is we can see u is right here. Right, that's u. And we can see that du is right here, 4x cubed dx. So now we can substitute. So this will be the indefinite integral of 1 over u squared du. All right, if I substitute for u squared and du. And now the advantage to that is this is a derivative we know how to take. Okay? a antiderivative we know how to do, because this is u to the negative second du. And the antiderivative of u to the negative second is u to the negative first over negative 1. Right? I just add 1 to the exponent and then divide by that exponent, plus c. So that's the opposite of 1 over u plus c. And now I can just substitute u back in so that I find I find this with respect to x. So this would be the opposite of 1 over x to the fourth plus 1 plus c. Okay, and so that's all there really is to the substitution rule. So the hardest thing about the substitution rule is figuring out what's the substitute. But for now, we're just going to practice doing this idea. Okay, so now let's try another one. So if I try the second one here, Okay, we have a u they're giving us, so the first thing you want to find is du. So the derivative of u with respect to, in this case, y, would be 4y cubed plus 8y dy. Okay. Now, what we need to do in order to be able to use this rule is we need this expression to show up, really this whole thing, to show up in the original problem. And we're kind of close to it, right? We've got y cubed plus 2y. So we need to multiply this by 4. Well, we have something like that in here, right? If I rewrite this as, rewrite 12 as 3 times y to the 4th plus 4y squared plus 1 times 4 times y cubed plus 2y dy. And then I distribute the 4. Then we get exactly what we're looking for, which is 4y cubed plus 2y dy. And so now we've got u right here, and we've got, sorry, I've forgotten a squared, so let me add that back in. This has been squared in both of those cases. So we've got our u, and we also have our du. So now we can substitute. So this would be the indefinite integral of 3u squared du, right? When I substitute for u and du. And now that's an antiderivative we know how to do, right? The antiderivative of 3u squared is 3u cubed over 3 plus c. And now we can simplify and substitute back in for u. So this would be the 3's cancel, and I substitute back in for u, which is y to the 4th plus 4y squared plus 1 cubed plus c. So there is our indefinite integral. Okay, so at this point, if you want to go and pause the video and try this first one here on your own, you can feel free to do that. This one is pretty similar to the ones we've done. Once you've tried this one, hit play. We'll go through it together, and we'll talk about these last two here that have a little bit more involved with them that we haven't talked about yet. Okay, so now that you've had a chance to try this first one, let's go through it together. So just like on the ones on the previous page, start by finding du. In this case, du, the derivative of 7x minus 1 would just be 7 dx. Okay, and so now in this indefinite integral, we can see both these parts. So we've got our square root of 7x minus 1 times 7 dx. So notice you've got u right here, and you've got du right here. So we can substitute, and we get the square root of u du. And we know how to do the indefinite integral of the square root of u by rewriting it as a exponent. So the antiderivative of u to the 1/2, you just add 1 to the exponent, so that would be u to the 3/2 divided by 3/2 plus c. So that's 2/3 u to the 3/2 plus c. And then we can substitute u back, substitute in for u. So this would be 2/3 times 7x minus 1 to the 3/2 plus c. Okay, so that's the idea. Now, in all of the examples so far that we've looked at, this one and the other two, du has been in the original problem exactly as written. But what if it isn't? What if when I find du, that doesn't show up exactly in the problem? Okay, well, let's look at a couple examples that go with that. So this second one here, you start off the same way. You find du. So the derivative of 2x squared is 4x. Okay, and then notice we've got an x in here, but we don't have a 4. So how do we add a 4 in? Well, we need to multiply by a factor of 1. So what we could redo is we could reorder this. So it's sine of 2x squared times x dx, right? So we've got this part of du in there, but we're missing the 4. So to get the 4 in there, we can just multiply by it. But if I only multiply by 4 like this, there's a problem, right? I've changed the value of this expression. It's now 4 times as large. So to undo that, we multiply by 1/4, right? Because 1/4 times 4 is 1, and so multiplying by 1 does not change the expression. So now we've got our du and we've got our u. So we can substitute. So this will be the indefinite integral of 1/4 sine of u du, right? So I just moved the 1/4 out in front. And so now we can do the antiderivative, right? The constant just stays the same. The antiderivative of sine is negative cosine u plus c. And so then we can substitute and multiply this, and we get the negative 1/4 cosine of 2x squared plus c. And so if you did and the way you would check any of these, which I haven't been doing yet, but let's just go and point that out here while I'm thinking about it. If you wanted to check this, you would do the derivative. So if I did the derivative of this with respect to x, well, the derivative, the negative 4 just stays out in front. I mean, negative 1/4 just stays out in front. And then we're going to have to use the chain rule. So the derivative of cosine is negative sine 2x squared. And I'm using the chain rule, so I have to do d dx of the inside, which is 2x squared. And the derivative of c is just 0, so plus 0. And then the derivative of 2x squared is 4x. So this would be negative 1/4 times sine of 2x squared times 4x. And then if you multiply this all together, so we lost the negative there. Negative times negative is positive. 1/4 times 4 is x, so we just get x sine of 2x squared, which is exactly what we started with, right? That's the original expression, so that checks out. So this is our indefinite integral. Okay, so that's the idea. So the same kind of thing is going to happen with the next one. And so that's kind of the change here, the thing that's a little more difficult. So with the last one here, you start out doing the same thing, right? So I find du. So du here is going to be, the derivative of 1 is 0. The derivative of the square root of x is 1 over 2 root x dx. And so in this problem, if I rewrite this a little, I've got 1 plus the square root of x times 1/3, to the 1/3, times 1 over root x dx. And so what am I missing here? Well, I'm missing this 2, right? I don't have that in the denominator, so I need to get that in there. So if I'm going to put a 2 in this denominator, I also need to put a 2 in the numerator. So we could rewrite this as 1 plus the square root of x times 1/3 times 2 times 1 over 2 root x dx. And now notice, these would cancel, right? So I haven't changed the expression value, I've just changed the way it looks. And so now we can substitute. So this would be 2 times u to the 1/3 du, right? Because this is du, this is u, and so we still leave to the 1/3 power and the 2. And so now we can do the antiderivative. So the antiderivative of 1/3, you just add 1 to the exponent. So this is going to be 2 times u to the 4/3 over 4/3 plus c. So that's 2 times 3/4 u to the 4/3 plus c. So that's 3/2 u to the 4/3 plus c. And then we can substitute u back in. So this is 3/2 times 1 plus the square root of x to the 4/3 plus c. Okay, so that's the idea of how this substitution rule works. Now where this gets a little trickier is when we don't tell you what u is, when you have to figure out what to make u. So in a lot of cases, u might be fairly easy. It's usually going to be an expression within one of the pieces, but not always. Sometimes it's going to be more complicated than that. So that's what we're going to look at now. Okay. So in this first case, it's fairly there's two really things you want to look for. So the first of all is you want to look for an expression within a function within a function, right? I want to look for, if I go back to the definition, this gx, right? That's what I'm looking for when I want to do the substitution. I'm looking for a function within a function. So really that gives us two options in this case. We could either do this square root of t that's on the bottom here and make it 1 over u, or we could do the square root of t plus 3 that's in the inside of cosine. And in this case, we want to go with this one on the inside, because when I take the derivative of that, I'm going to get this expression similar to the one on the outside. When I take the derivative of the inside of cosine, I'm going to get something similar to this, which is part of the process. And you can always guess and check, right? So if I guess that u is the square root of t plus 3, then when I do du, the question is, do I get something that's going to help me simplify what I'm looking at on the outside? So the derivative of this would be 1 over 2 times the square root of t dx, right? If I take the square root of the square root of t, the derivative of the square root of t plus 3. Okay? And notice this expression is similar to this one, right, that we already saw. So we're going to be able to use that. So that's a good thing for you. So let's rewrite this in the order of f of u du. So this would be the cosine of the square root of t plus 3 times 1 over the square root of t dt. And now I need to get the 2 into the problem. So this would be cosine of the square root of t plus 3 times 2 times 1 over 2 root t dt. And so now I can do the substitution. So we can replace square root of t plus 3 with u, and we can replace 1 over the square root of t dt with du. Right, this should be a dt, sorry. Up here at the top of the problem, the variable in this problem is t, so we want to use dt. So du. And so now we know how to do this antiderivative. So the antiderivative of cosine of u is just sine u plus c, and the 2 just comes out in front, right, because it's a constant multiple. And now we can substitute u back in. So this is 2 sine of the square root of t plus 3 plus c is our indefinite integral. Okay, and so that's the idea. So in the second problem here, you have a lot of options on what things you could substitute. So what you want to be thinking about, remember, is what thing can I substitute for that when I take the derivative, I will get something similar to something else in the problem. So in this example, the key thing to notice here is that we're dealing with tangents and secants. So if you remember, the key here is the trig derivatives. Well, the derivative of tangent is secant squared. So that gives you a pretty good idea that we want to let u, and I'm going to go ahead and just change colors here so this is a little easier to see which is which problem, u be the tangent of x over 2. Okay. So that'll give us a pretty good place to start here. Because now the derivative of u is, well, we have to use the chain rule. So we start by taking the derivative of the whole thing. Well, the derivative of tangent is secant squared of x over 2. And the derivative of x over 2 is 1/2 dx. Okay, so that's what we get for du because we took the derivative of that. Okay, so now once we've done that, what we want to do is we want to take the rewrite this using this expression, which is, we're already in a pretty good place with it, but we need to add in this 1/2 power. So this would be tangent to the 7th power of x to the 2nd times 2 times 1/2 secant squared x over 2 dx. Right, to get this 1/2 in, I need to add the 1/2, but I also need to multiply by its reciprocal so that I'm not changing the actual problem. Okay, so now we can start doing this. Now we can do the substitution. So u is tangent of x over 2, so that means we'll get u to the 7th times 2 times du. And so that's the antiderivative of 2u to the 7th du. And so that antiderivative is 2 times u to the 8th over 8 plus c. So that's u to the 8th over 4 plus c. And now substitute tangent back in. So this is tangent of x to the x over 2 to the 8th divided by 4 plus c is our definite integral. Okay, so that's the idea. And sometimes this is so hopefully you guys are all okay with that so far. Okay. Now, sometimes this is going to be even a little bit more difficult to figure out what u should be. Those are a little bit more straightforward. Figuring out what u should be. The first one I think is the most obvious. The second one's a little trickier because you just have so many options and trying to figure out the best one. But always remember, try to figure out what you would like when you take the derivative of what you let u be, what you're going to get. Now, in this last one here, there's even another kind of tip we could use to help us with these. So in this case, I think it's fairly obvious what a good idea for u would be. We want to do the thing inside the square root. So u equals 4 minus x, which means that du is just going to be -1 dx. Now, notice that still leaves us with this x, but we can actually do a little bit more substitution to help us with that as well, because if u equals 4 minus x, well, we could solve this for x. So then subtract 4 from both sides. Okay, so u minus 4 equals the opposite of x, and so that means 4 minus u equals x. Okay, and so that's going to allow us to do a little bit more substitution here. Okay, so we need to get that -1 in here too. So what we want to do is, first of all, we're missing this -1, so let's make this the x times 4 minus x, and so we're going to need to multiply -1 times -1 dx, right? So now I've got -1 times -1 is just 1, so it's fine to add those in, and this is du. So now we do our substitution. So this would be, for x, we substitute 4 minus u. For 4 minus x, we substitute u, and then for -1 du, we substitute dx, we substitute du. And so now, sorry, I forgot, I missed a -1 there. So we still, this -1, the first one, sticks around, and then we get du for -1 times dx, right? Because that's what du is. And so now what we want to do is some simplification inside here. So first of all, if you take -1 times 4 minus u, you get u minus 4. And now what I want to do is I want to multiply these together, which is something I can do with what I have here now and turn it into a polynomial. So this would be the antiderivative of u minus 4 times u to the 1/2 du. And now we can distribute. So this is the indefinite integral of u u times u to the 1/2 is u to the 3/2 minus 4 u to the 1/2 du. And now that is something we can take the antiderivative of, because those are just terms to an exponent. So to do the antiderivative u to the 3/2, we add 1 to the exponent, so that's u to the 5/2 over 5/2, and then minus 4 u to the 3/2 over 3/2 plus c, and now we can simplify, so this is 2/5 times u to the 5/2 minus 4 times 2/3 u to the 3/2 plus c, which is 2/5 times 4 minus x to the 5/2 minus 8/3 times 4 minus x to the 3/2 plus c. Okay, and that's all there is to that. So that's one of the things you have to be a little bit careful with here, is sometimes you can substitute for u twice, substitute in 2 different ways to get u into your problem, and that's what we had to do here. Okay, so that's the idea of using the substitution rule. So when it comes to using the substitution rule, similar to the chain rule, it's just all about practice, doing as many problems of these as you can, and just guessing and checking until you figure out a u that will work. Okay. So what I'd like you all to do at this point is pause the video, try these 3 problems on page 30, and then when you hit play on the video, we'll go through these, and we'll see what you guys will go through them. Okay, so the first one, I think you want to use u equals 5s plus 4, right? Just let it be the bottom. So that means inside the radical. So that means du is 5 ds. And notice I pick something. Whenever we pick something here, we want u to make this into a function that is something we know how to deal with. Well, we know how to do the antiderivative of 1 over the square root of x, right? Because that's just an exponent. We can write it as an exponent. We know how to do antiderivatives of exponents. So that's why substituting for the 5s plus 4 will be helpful to us. So now what we're missing in this problem, though, is this 5. So that means I'm going to need to put those in. So this will be the indefinite integral of 1 over the square root of 5s plus 4 times 1/5 times 5 ds. And so now I've got my du in the problem. So now we substitute, and this will be 1 over 5 times the square root of u to du. And now I'm going to rewrite this as an exponent so that it's easier to do the antiderivative. So the square root of 1 over the square root of u is u to the negative 1/2 du. And so now we can do the antiderivative, just add 1 to the exponent. So this is 1/5 times u to the 1/2 over 1/2 plus c. And now we can do some simplification. So this is 1/5 times 2 over 1 times the square root of u plus c. So that's 2/5 times the square root of 5s plus 4 plus c is our indefinite integral. Okay, so that's the idea there. Okay, so for the next one, we want, this one is very similar to the one we did before. So we know that the derivative of tangent is secant squared. So if I let u equal tangent of x, then du is secant squared of x dx. And so now this substitutes in pretty easily, right? Because we've already got secant squared x dx in the problem. So this is the indefinite integral of u squared du. That antiderivative is just u cubed over 3 plus c, and now substitute u back in. So this is tangent cubed of x over 3 plus c. Now the last one probably needs to start with some simplification. So this one is set up a little trickier, but we do know part of what's going on here. So the square root of x to the fourth is just x squared. So you could rewrite this as x squared over x cubed minus 1 dx. And that actually makes it easier to do the substitution. Because if I let u equal x cubed minus 1, I'm going to get something involving an x squared, because du then is 3x squared dx. And so now the x squared is in there, so if I rewrite my indefinite integral as 1 over the square root of x cubed minus 1 times x squared dx, all I have to do is get this 3 into the problem, because I already have the x squared dx. So that's going to be 1 over the square root of x cubed minus 1 times 1/3 times 3x squared dx, and now we can do our substitution. So this will be the indefinite integral of 1 over the square root of u times 1/3 du, and we already know how to do this antiderivative, right? We did it at the top, but I'll go ahead and write it out. So this will be 1/3 times u to the negative 1/2 du, and the antiderivative, to do the antiderivative, we just add 1 to the exponent. So this would be u to the 3/2 over 3/2 plus c, and so this is 1/3 times 2/3 u to 3, sorry, it's not 3/2. I'm going, if I add 1 to the exponent, it's 1/2 over the 1/2, so 2 over 1 plus c. So this would be 2/3 times the square root of u plus c, and then when I substitute u back in, it's 2/3 times the square root of x cubed minus 1 plus c is the final answer. Okay, so that's the idea. So that's where the chain rule, the substitution rule comes into play here. So it's going to allow us to do a lot more derivatives than we were able to do. I mean, a lot more indefinite integrals than we were able to do before. So beyond, once you know how to do antiderivatives, what this leads to is doing initial value problems. So that's what we're going to look at here, is doing some initial value problems that involve the substitution rule. So when you go to do an initial value problem, remember, solving one means to find the original function given a derivative or second derivative or third derivative and some values of the function for those. So if I start out with the second derivative of y with respect to x, which is what I've been given here, and I want to solve the initial value problem, that means I want to find y. I want to find the function y by working backwards. So we start off by doing the first antiderivative here, by doing, So if d squared y over dx squared, the second derivative equals this, then the first derivative, dy dx, will equal the indefinite integral of 4 secant squared 2x tangent 2x dx. Okay, it will be equal to the indefinite integral of that. So now we're just going to use the substitution rule to find that first derivative. So we can use some of the stuff we've already talked about, which is we know that secant squared is the antiderivative, is the derivative of tangent. So if I'm going to substitute for one of these, I'm going to want to substitute for tangent. Okay, so if I let u be tangent of 2x, then du is secant, if I take the derivative of that, I get secant squared 2x, and then times the derivative of the inside, because I have to use the chain rule, so it looks like this. Okay, and so we already have a 2 built in here, so if dy dx is going to equal, and I'm going to rewrite this so that I can do this substitution. So this is going to be 2, because I need to steal a 2 from this, tangent of 2x times 2 secant squared 2x dx. And so now I have my du, And so I can do my substitution. So dy dx is going to equal the indefinite integral of 2u du. And now I can do that antiderivative. So dy dx will equal 2 times u squared over 2 plus c. So dy dx equals u squared plus c. Or actually, let me go ahead and I need to save some space. So let's go ahead and substitute tangent back in there. So tangent squared 2x plus c. Okay. Oops, I forgot a 2. So 2 tangent squared 2x plus c. And now we plug in our values so that we can figure out what c is. So this would be 4 equals 2 times the tangent squared of 2 times 0 plus c. Well, tangent of 0 is just 0. So this would be 0 plus c, so 4 equals c. So our function is dy dx equals 2 tangent squared 2x plus 4. Okay. Now, that's a good start. We did this once. Now we have to do it again. Now, this one we run into a problem because I can tell you right now as we go to start this problem that we don't know. Okay, so now let's just go ahead and start setting up. So y equals the definite integral of 2 tangent squared 2x plus 4 dx. But now we're kind of into a problem because whatever substitution I try to do here, I'm not going to run into something I know how to do the antiderivative of because I don't know how to do the antiderivative of tangent squared. However, I can... Did I? Oh, whoops. I put a 2 in here when I should not have. Yeah, those 2's cancel out. I was right the first time. So let me go back a second. These 2 2's cancel out, and now we're good. Okay, but now we're good. But I still can't, no matter what I substitute for here, I'm not going to be able to simplify this because if I substitute, let's just write a couple out. If I let u equal 2x, then du is 2, which seems like it might be okay, except then I'm going to have to find the antiderivative of tangent squared of u, which I don't know how to do. We don't know what the antiderivative of tangent squared is, so that's not going to work. If I try to do u equals tangent of 2x again, the problem with that is when I go to find du that I get secant squared, and I don't have a secant squared in the problem, so that's not going to work. But what we can do is use a trig identity to substitute here to give us something that does work. So one of our trig identities is that tangent squared of x equals secant squared of x minus 1. And I do know the derivative, the antiderivative secant squared x. So if we substitute, so that this is secant squared of 2x minus 1 plus 4 dx. So this is y equals secant squared of 2x plus 3 dx. Now we can actually do the rest of this problem by using substitution. Okay, so if I substitute in let u equal 2x, then du equals 2. And so that means I'm just going to need to cancel out that 2, right? Because there's no 2 in the problem. So we're going to have to multiply by 1/2. So this would be y equals the antiderivative of secant squared 2x plus 3 times 1/2 times 2 dx. And now we can do the substitution. So this would be y equals the indefinite integral of secant squared u plus 3 times 1/2 du. Okay, and now I can do these antiderivatives. So the antiderivative of secant squared u is just tan u. The antiderivative of 3 is 3u. Okay, and the 1/2 is just a constant. So times 1/2 plus c. Okay, and so now we substitute back in for u, and this will be tangent of 2x over 2 plus 3 times 2. And if I substitute 2x in here, the 2 will cancel, so this will be 3x plus c. And there's our final answer. Oh, except I'm not actually done yet. I need to plug in 0. So if I plug in 0, because this is an initial value problem, so if we plug in 0 here, 0, this first one will be 0 because tangent of 0 is 0. 3 times 0 is 0. So in this case, c is -1. So our final answer would be tangent of 2x over 2 plus 3x minus 1 is our final answer. Okay. So that's the idea. So let's go ahead and try another one. So that one was pretty complicated, mostly because of having to substitute for trig identities and things like that. But they don't have to be that complicated. So the next one says the acceleration of a particle moving forward and back on a line is a equals d. The second derivative, which is the acceleration, is the same thing as the second derivative position, equals pi squared times cosine of pi t for all t if s equals 0 and v equals 8 meters per second when t equals 0. Find s when t equals 1. So the first thing you have to do is you have to find s. Okay, so to do that, we start off with d squared s over dt squared. So the second derivative equals pi squared cosine of pi t dt. Okay, and so we do, to find ds dt, we are going to find the indefinite integral of this. Okay. So we're going to need to use substitution. So the most, I would use u equals pi t. So that means du equals pi dt. And so I could rewrite this as ds dt equals pi cosine of pi t times pi dt. So if I split up these two pi's, I get this. And now here's my u, du, and my u. And so this would be ds dt equals the indefinite integral of pi cosine of u du. Okay. And then we do the antiderivative of that. So the antiderivative of pi cosine u would be pi sine u plus c. And so then we can substitute. So ds dt equals pi sine of pi t plus c. And so now we need to figure out what c is. So velocity is 8 meters when t is 0. So 8 equals pi times sine of pi times 0 plus c. Sine of 0 is 0. So 8 will equal c. So ds dt equals pi sine of pi t plus 8. Okay, and so now we need to do, we're trying to find s, so we need to do the antiderivative. We need to do the indefinite integral again. So s is going to equal the indefinite integral of pi sine of pi t plus 8 dt. Okay. So once again, it's going to make sense to let u be pi t. So du is du is pi. And actually, one of the things you can do here before we do that step is you could break these into two separate pieces, because remember, when you're doing antiderivatives, you can do them separately. So this will be s equals, we already have a pi here, so this will be s equals the antiderivative of sine u du plus the indefinite integral of 8 dt. And then we can do those. So s equals, the antiderivative of sine is negative cosine u plus the antiderivative of 8 dt is 8t plus c. And now we can substitute in the value for u, what we substitute, which is pi t. So sine equals negative cosine pi t plus 8t plus c. And now we need to find c. So you plug in the value for s. S was 0 when t is 1. When t is 0. And so in this case, pi of 0 is, cosine of 0 is 1, so that's negative 1. 8 is 0, so this is 0 equals negative 1 plus c. Add 1 to both sides, so c equals 1. So s would equal negative cosine of pi t plus 8t plus 1. And now you can just substitute 1 in for t. So negative cosine of pi is negative 1. Negative 1 is negative, the opposite of negative 1 is 1. Plus 8 plus 1, so that's 10. So when t equals 1, s equals 10 meters. Okay. And so there is the answer to that problem. Okay. So at this point, go ahead and flip over to the next page and pause the video and try these. The first one at least is slightly easier because it doesn't involve trig functions, but both of these I think should be pretty straightforward. But notice in both of these cases, I only gave you the first derivative, so you don't have to do everything twice like we did in that page. So go ahead and pause the video, try these two, and when you hit play, we'll go through them together. Okay, so for this first one, just let u equal x squared plus 8. So then du is 2x dx. So when we're when we want to go find y, that's going to be the indefinite integral of we need a 2 for du. So I'm going to break 4 up into two pieces. So this would be 2 times x squared plus 8 to the negative 1/3 times 2x dx. Notice that this is exactly the same as the problem up here, except I just broke the 4x into two pieces, 2 and 2x. And so now I've got my u and my du. So this is y equals 2 times u to the negative 1/3 du. And now we can do the antiderivative. So y equals 2 times we add 1 to the exponent. So negative 1/3 plus 1 is u to the 2/3 over 2/3 plus c. So this is y equals 2 times 3/2 times u to the 2/3 plus c. So this is y equals 3 times x squared plus 8 to the 2/3 plus c. And now we can plug in our expression to figure out what c is. So this would be 0 equals 3 times 0 squared plus 8 to the 2/3 plus c. So that's 0 equals 3 times 8 to the 2/3 plus c. So 8 to the 2/3 is 4. So this would be 3 times 4 plus c. So 0 equals 12 plus c. So negative 12 equals c. So this would be y equals 3 times x squared plus 8 to the 2/3 minus 12. Would be the original function. Okay, so that's the idea there. Okay, now in the next one, you might have originally thought, well, let's just use pi over 4 minus theta for our u. But the problem with that is we don't really know how to do that. Leaves you with a cosine squared, and we don't know the antiderivative of cosine squared. We know the antiderivative of cosine. So what we probably want to do is, and we know the antiderivative of something squared. So what we probably want to do is let u equal cosine of pi over 4 minus theta. And then that means du is, well, the derivative of that is you do the derivative of cosine. Derivative of cosine is negative sine negative sine no, that's not going to work either. Hold on 1 second. Okay, actually, I think there's a typo in this one, so let's just go ahead and skip this one, and we'll call that the end of this section. So there's another example. So that's it for today. Don't forget to do your homework, and if you have any questions, feel free to text, call, or email me, and we can go over any questions you might have on these assignments.